So we're going to start with the very basics. The basics are we're going to start with redox equations and oxidation states. The first, redox. Redox is oxidation and reduction. So when you have both things happening, so what is oxidation? Oxidation is the loss of electrons. It's when something loses electrons, that is what oxidation is. It's the loss of electrons, and when something loses electrons, its charge increases, which we're going to call oxidation state. So the oxidation state increases. And vice versa, you have reduction. Reduction is, so we'll quickly do the balancing of redox equations, and then we're going to move towards A2 redox reaction. So first we're going to revise. So reduction is a gain of electrons, and that is the oxidation state decreasing. It becomes lesser. You become more negative when you gain electrons. So the oxidation state, it decreases. So everything has charges on it, which we're going to call oxidation states. So if you're going from, so one second, if you're going from like if you have -3, -2, -1, so different substances will have different oxidation states. One, this is +1, +2, +3, and one second. So you're going to have charges +3. So no matter what the charge is, if the oxidation state increases, that is oxidation. So you're going from -2 to -1, or 0 to +1, or +1 to +3. That is oxidation, and vice versa. If you're going downwards, if you're becoming more negative or going towards the negative side, that means reduction is happening. So that is reduction. Now, the first very quick point is what's the difference between oxidation state and the actual charge? So the thing is that oxidation state is the charge on the element if the compound is, or you're treating it as if it's ionic. So it's the charge on the element So it's the charge on the element, and it's not always the actual charge. I'll explain what that charge is. It's different from a charge. So it's a charge on the element if the molecule or compound is treated as if it's ionic. Sometimes it will be ionic, sometimes it's not going to be ionic, sometimes it's going to be covalent. So molecular compound is treated as if it is ionic. So elements don't always have charge, especially in molecules. So for example, if you have, first thing is we'll talk about electronegativity. I'll explain the difference between ionic and covalent molecules very, very quickly. So electronegativity increases to the right, which is the tendency for an atom to gain electrons. It increases to the right and it increases upwards. Smaller atoms, their nucleus are less shielded, which is why they attract electrons very strongly. There are a number of reasons why electronegativity increases on this corner over here. You move away from this corner, the electronegativity starts to decrease. So one of the reasons why electronegativity increases to the right is that the atom has more protons. When you move to the right, you have more protons. So the nucleus is more positive. So obviously there's going to be more attraction for electrons. Fluorine over here has 9 protons. Lithium on the other side has 3 protons. So obviously fluorine with 9 protons has a much stronger attraction for electrons. And the other thing is when you move up the group, the atom is less shielded. Its nucleus is not covered by that many electrons. So the nucleus has a more effective attraction for electrons. Bigger atoms like iodine over here at the bottom already has 53 electrons. So its nucleus is already surrounded by many electrons. Like 53 electrons is a huge number. So its nucleus would be too shielded to attract more electrons. So down the group, the electronegativity decreases. But anyways, hopefully if you're done with AS, electronegativity increases to the right. These are the more electronegative elements. So you've got all sorts of compounds. Sometimes the elements are the compounds are ionic. When do you have ionic? Ionic compounds are when you have a large difference in electronegativity. So whenever you have a very large difference in electronegativity, you get an ionic compound. So for example, when you have large differences in electronegativity, when one of the atom is not very electronegative, that means it's not really interested in its outer shell electrons, it's not attracting those electrons. And the other element on the right side is extremely electronegative. So what happens is that one of the atom ends up losing electrons, the other one ends up gaining electrons. One of them becomes +1, the other one becomes -1. So everyone pretty much knows this. But for ionic compound, you need a very large difference in electronegativity. That's why one of the atom would lose electrons, the other one would gain electrons.
NaCl में large electronegativity.
नहीं, Cl के अंदर large है.
Like
नहीं, sorry,
दोनों
NaCl has a large difference in electronegativity. Like one of them is on the extreme left side, so that is not very electronegative. The other one is on the extreme right side, that is extremely electronegative. Clear है? अच्छा, so basically this is your extreme end. There's an extreme end which is ionic. Then you have the other extreme end, which is a perfectly covalent molecule. So let's talk about a perfectly covalent molecule. Now, when you have a perfectly covalent molecule, what that means is there's absolutely not going to be any difference in electronegativity. So you have two atoms joining up, and there is no difference in electronegativity. So one example is, what if you have two fluorines? So that is going to be, two fluorines bonded to each other, which means that they're sharing electrons. The reason they're sharing electrons is the reason why these electrons are stuck in the middle is because both of them have exactly the same electronegativity, which means one of them is trying to pull electrons towards itself. The other one is also trying to pull those electrons towards itself. And just like a tug of war, if both of them are pulling electrons with the same strength, then the electrons would stay exactly in the middle. No one ends up gaining electrons, no one ends up losing electrons. So instead, they share electrons. So that one is a perfectly covalent molecule, and the two forces of attraction are going to get cancelled out. Okay? So just think of it as two people fighting over electrons, and they both are pulling the electrons with the same force. So the electrons are going to be right in the middle, neither to the right, neither to the left side. Okay? Is this point clear as well? You've got a perfectly covalent molecule with no difference in electronegativity. Okay, is this clear?
Yes, sir.
Then you have things that are kind of in the middle. these are known as polar covalent molecules. So remember, there's a spectrum. It's not that something is completely covalent and something is completely ionic. There's a lot of in between things. So you've got polar covalent molecules. And in polar covalent molecules, there's going to be a slight difference in electronegativity. So not a large, but just a tiny bit, or there's going to be just a slight difference in electronegativity. So not a huge one, but just a slight one. So one example is your HCl molecule. So if you look at an HCl molecule, in an HCl molecule, the electrons, Cl is slightly more electronegative. So the difference is there, but not very large. So electronegative. So Cl is just slightly more electronegative. What that does is that the electrons are slightly closer to Cl, which is why it gets a very slight negative charge and the H gets a very slight positive charge, which is basically a dipole. So you've got this spectrum. So nothing is completely ionic. I mean, although the extreme versions, this is one end, one extreme end, and this is the other extreme end. But a lot of molecules would be kind of in between. There would be polar covalent molecules. So the thing is that you have this spectrum. Now, when you talk about oxidation state is the charge on the molecule if the molecule is behaving as if it's an ionic compound. So when you talk about oxidation state, we are interested in the fact, I mean, what was the definition of oxidation reduction? Oxidation is the loss of electrons, reduction is the gain of electrons. Now over here, especially in molecules, we don't really care who gains, I mean, we don't really care whether they're gaining electrons just very slightly. For example, over here, Cl is only attracting those electrons, but partially. Like it's not able to pull those electrons completely towards itself. But when we talk about redox reactions, we don't care about that. I mean, you had two electrons over here. Where, I mean, which of the atoms out of the two is gaining electrons? Which one out of the two is losing electrons? So it's H that's losing electrons. I'm going to call H as +1. I'm going to treat this molecule as if it's ionic. So I'm going to treat it as if Cl has gained all the electrons. So I'm going to call H as +1 and I'm going to call Cl as -1, which are not the actual charges, but we're not really interested in the actual charge. We're just trying to figure out who's gaining electrons and who's losing electrons. -1 indicates that it has gained electrons, although the actual charge is slight negative, but I don't care about the actual charge. I just want to know which side are these electrons going towards, this side or this side. So if they're going towards this side, that means this is -1. So remember, Cl is only gaining one of the electrons because the other electron was its own electron. So that wouldn't be counted. It's gaining one electron. And H is only losing one electron because the other electron was, I mean, it belonged to Cl already. So H is basically only losing one of its electrons. So H is +1. Over here, no one ended up gaining or losing electrons. So we're going to call that as zero charge because no one ended up gaining or losing electrons. So I'm going to give it an oxidation state of 0. And then when it comes to ionic compounds, then the actual charge is the oxidation state. Na is +1, Cl is in reality it is -1. So this is how oxidation state is different from the actual charge. The actual charge could be slight positive, slight negative, but when you talk about oxidation state, we're just trying to figure out are these two electrons closer to Cl or are these closer to H? We don't care whether it's slight negative or slight positive. I'm just going to give these electrons to Cl and call it -1. That in this molecule, Cl is the one that's gaining electrons and H is the one that's losing electrons. So this is how you figure out oxidation states, which are based on electronegativity. For example, Here's another molecule, and it's an oxygen with 2 fluorines. So in this molecule, fluorine is one of the most electronegative elements. Fluorine is right in this corner. I mean, this corner belongs to fluorine. So it's right over here, above Cl. So nothing is more electronegative than fluorine. So I've got this atom, this molecule, and although it's a covalent molecule, these electrons would be closer to F. So I'm going to treat it as if it's ionic. I'm just going to say that fluorine is the one that's gaining electrons. So fluorine would be -1. These electrons would be closer to fluorine as well. So I'm going to call fluorine as -1, and oxygen is the one that would be having a charge of +2 because I mean these electrons would be closer to F. So oxygen would be the one that would be losing 1 electron over here and one of its electrons to this one. So which is why it's going to be +2. So is this clear, the background of oxidation states?
Yes, sir.
TK, Sam, is this clear, Nadine? So now that's just the background, TK. So remember, oxidation state is not the actual, it's not the actual charge. It's just that you're trying to figure out who's gaining electrons, who's losing electrons. And we don't care whether they're gaining it partially or whether they're gaining it completely. I said now using oxidation state to figure out I mean the charges. So using electronegativity to figure out oxidation state is time consuming. So the easy method is you can simply use a table using which you can calculate the oxidation states. So any neutral, the first rule for those, or the shortcut for figuring out oxidation state, is that any neutral element, sorry. So any neutral element, the oxidation state, I'm just going to call it O dot S, is going to be 0 for a neutral element. Then you have, so that's the first thing, any neutral element oxidation state is 0. If it's an ion, so for ions, the charge is the oxidation state. So if Na is +1, then its oxidation state is +1. So we're going to talk about compounds now. When you have compounds, now ions are present in compounds. So we're going to talk about group 1. In compounds, group 1 is always +1. Group 2 similarly is always +2. Group 3 is going to be always +3. And then you have transition metals, which are going to have variable. I mean, they're going to have variable oxidation states. So for them, it's going to be, as it's going to be variable. And then you have the other ones of non-metals. Fluorine, remember, is always -1. But you don't have a lot of compounds that contain fluorine. So that's, in most cases, that is kind of irrelevant. You won't even use it in most cases because most molecules don't have fluorine in them. But they do have oxygen and hydrogen. So oxygen is -2, but with some exceptions, except in H2O2. Where it's actually -1. And another one which is or with fluorine. So or with F. So then hydrogen is +1 most of the time. except with metal hydrides, except in metal hydrides. So in metal hydrides, what happens is that you got, like if you have NaH, Na would be the one that would be +1 and H would be the one that would be -1, because metals are the least electronegative elements, so they always lose electrons. So this is all that you need to figure out oxidation states. So we're going to figure out or learn how to figure out, most of you already know this. So we're going to quickly figure out oxidation states of few elements. The way you're going to do this is, like if you have SO4, which is -2, then for oxygen, you already know that. For sulfur, you don't know what the oxidation state is. Sulfur is unknown. So sulfur is, I mean, we're going to just call it S. We don't know what the oxidation state of sulfur is. For oxygen, if you look at the table, the oxidation state is already given, that's -2. And there are 4 oxygens in this, so it's -2 times 4. And the whole ion has a charge of -2, which means that the individual charges must add up to be equal to -2. So if I make sulfur the subject of the equation, it comes out to be what? +6, I think. So that means sulfur's oxidation state over here is +6. So sulfur's oxidation state is +6, while oxygen was -2. We can do another one. Let's say I have H3PO4. So I already know what H and O are, but I have no idea what P is. So H is +1 times 3 because there are 3 of them. Phosphorus, I have no idea. So I'm just going to write P over here. And the other one is -2 times 4. Oxygen is -2. And it's a neutral molecule. It's a neutral molecule. So in a neutral molecule, all the charges must add up to be equal to 0. If you solve for this over here, this -8 would go to the other side and it would become +8. And +3 would go to the other side, it would become -3, and this comes out to be +5. And so you just have to add up the individual charges and make it equal to the total charge. Here's another one, ClO3 -1. So in ClO3 -1, you've got Cl as the unknown. No idea what that is because it's not given in the table. Oxygen is -2. And there are 3 of them. And they should all add up to be equal to -1. If you solve for x, this comes out to be equal to plus. It would come out to be equal to +5. So that means Cl over here is +5. Oxygen was -2. So is this part clear? Tika, you're all familiar with this. Is this clear?
Yes, sir.
Yes.
So Tika, so we're not going to practice this a lot. It's something very basic. So we're going to move to the next thing, which is just 1 second. So we're going to move. So we're going to move to the next thing, which is balancing redox equations. So before starting with electrochemistry, this is something that's very, very important. And that is balancing redox equations. So balancing redox equations. Now, redox equations are when one substance loses electrons and the other substance ends up gaining electrons. So here's one example where you have sodium reacting with Al3 plus, and it produces Na+1. And aluminium gets reduced. So N is the one that's getting oxidized. Remember, charge increasing, that's oxidation, 0 to +1. So that is oxidation. Whenever the charge increases, you're going to call it oxidation. And it loses exactly 1 electron. And Al, on the other hand, goes from +3 to 0. So that means the charge is decreasing. That's reduction. And reduction is a gain of electrons. In this case, it's going to be 3 electrons because you move from +3 to, I mean, you had +3 over here, now you have 0 over here. So basically, you're gaining 3 electrons. Now, whenever you have a redox equation, the thing that's important is you have to do 2 things. The first thing is you've got to balance the number of electrons gained and lost. Gain and loss. You got to somehow make them equal. So that's the first thing. And then you have to, the next thing is you got to balance the atoms. So balance the atoms the normal way. So over here, what you need to do is the number of electrons gained and lost are not equal. Over here, it's 3 electrons. Over here, it's 1 electron. So what you can do with this 1 electron is you can multiply it by 3 and the number of electrons gained and lost would become equal. So that requires 3 sodiums and 3 sodium +1 ions. And now your equation is balanced. The number of electrons gained and the number of electrons lost are now equal. Previously they weren't, now they are. Okay, is this part clear?
Yes, sir.
And we can quickly do one second. So for example, I have this reaction. If he changes to 2+ and copper changes to 2+ as well. So I have this reaction. I need to balance it. I need to balance it atomized as well as I need to make the number of electrons gained and lost equal. Just a second. वो भी कर लेते हैं. One second. ठीक है. अच्छा, so this one, first thing is but I'll just balance it the usual way. One second, किसी का mic on है. So the first thing is you got to Fe3+ is getting reduced, charge decreasing, that's reduction, that's a gain of 1 electron. And the other thing, copper goes from copper to copper 2+, that's a loss of 2 electrons, that's oxidation. So you need to make them equal. So only thing you need to do is you multiply the Fe1 with 2. And that's about it. That's the only thing you had to do. You had to make the number of electrons gained and lost equal. So you did that. Okay, so now that's a simple step that you need to do. Okay, somebody asked me to do half equation, so I'm going to do just that. What's happening here is Fe3+ changing into Fe2+, that is gain of electrons, that's the reduction equation. So you can write or convert this equation into 2 half equations. You can separate the 2 equations into a reduction equation. The reduction equation is 2Fe3+. They're turning into 2Fe2+. And in the process, they're losing 2 electrons. Or, I mean, sorry, in the process, they're gaining electrons. Okay, this is a gain of 1 electron. So they're gaining electrons. So I'll just move this further to the right, and that's a gain of 2 electrons. And then you can separately write the oxidation equation where they're losing electrons. Now, if I write the oxidation half equation, that is the first one, copper turning into copper 2+, and it's losing 2 electrons. So copper is turning into copper 2+. And in the process, it is losing 2 electrons. So I've written down my 2 half equations as well. Isa, is this clear?
Yes, sir.
So anyway, so the simple equations, is this clear? Simple equations, gain electrons, loss of electrons. You got to make them equal. So you got to multiply one of them by a certain number. In this case, I multiplied this by 2, which means I multiplied Fe by 2 and Fe2+ by 2 as well. TK, is this clear? Bhaskar, is this clear? Hafsa?
Yes, sir.
TK. So the next part is I'm going to move towards slightly more difficult equations. So, and I would have to copy them from somewhere. Just a second. So we'll do a couple of a bit more difficult equations. So I'm going to just copy these equations. So you just give me 1 second while I copy one of the equations. So I've got this equation Cr2O7 2-. You probably can't see this on the screen. I'm writing it. And it's HNO2 plus there's H+1, and the products are Cr3+, and there's another product which is NO3-1, and then there's H2O.
So we can't see.
Okay, just a second. Let me. Asha, here's the reaction. Okay, so it's exactly, we're going to do exactly the same thing. Here's my equation. Now the only thing is, it's not that straightforward anymore because they didn't give you the oxidation state. They've given you the formula of the entire compound. So the first thing is, you're going to try and figure out what the oxidation state is because the charges are not written. I mean, you've got this entire thing, Cr2O7, 2-. So what is the charge of the elements? Who's getting oxidized? Who's getting reduced? So we're going to start with the Cr2O7, 2-. Now I know that oxygen is -2 according to the table. For chromium, I have no idea what chromium is. So I'm going to take chromium as X. And there are 2 of them, so that's 2X. Oxygen is -2 according to table. So -2 times 7. And the entire ion has a charge of 2-. So that means if I try and calculate for X, X would be -14 goes to the other side, that's 12. And then 12 would be divided by 2 because they're 2X, and this comes out to be +X. So that means chromium over here is +X. And oxygen by default is -2. Oxygen is always -2. Then the next one, you've got HNO2. Now in HNO2, I know that H is +1. I know that oxygen is -2. No idea what N is. So I'm going to try and find out this one, what N is. So I know that H is +1. I had no idea what N is. So I'm going to take that as X. Let me just take this further. So I'm going to take that as X. Oxygen is -2 and there are 2 of them. And the whole thing, all the charges, they must add up to be equal to 0 because it's a neutral molecule. And if you solve for X, it would be -2 goes to the other side. So that's +4, -1, and it comes out to be equal to 3. So that means N over here is plus 3. So I figured out what N is. H is already plus 1, so that's, I mean, the charge on the ion is the oxidation state. Cr is already plus 3, so that's plus 3. Then we come to NO3 minus 1, so no idea again what NO3 minus 1 is. So we're going to calculate NO3 minus 1 quickly. So N is X, oxygen is minus 2 times 3. The whole thing must add up to be equal to minus 1. You solve for X, it will be minus 6 goes to the other side, it becomes plus 5. So N over here is plus 5. And oxygen by default is minus 2. And then you have H. H and O we already know. So that's an additional thing that we had to do. We had to figure out what the oxidation states were. I'm just going to. Is this part clear? Sam, Nadine, is this clear?
Yes, sir.
So now the final thing is you got to make the number of electrons gained and lost equal. So the first thing is you have to figure out, let me just take this to the side. So the first thing you got to figure out is who's gaining electrons, who's losing electrons. So anything that's getting reduced, that is the one that's gaining electrons, which is obviously Cr in this case. It's going from plus 6 to plus 3. So that's gaining of 3 electrons. And we're talking about 1 Cr at the moment. Do you remember when you talk about oxidation states, you're talking about one of the atoms or ions. N on the other hand goes from plus 3 to plus 5. So that is oxidation taking place. And that's exactly a loss of, so that one is a loss of 2 electrons, plus 3 to plus 5, right? So it's a loss of 2 electrons. You got to make the number of electrons gained and lost equal. So I'm going to pick a number, multiply this with 3. And I'm going to multiply this other one by 2. What that means is I need 3 n's. I need there to be 3 n's. So I'm going to multiply this by 3. So I have 3 n's over here. I'm going to multiply this by 3 so that I have 3 n's over here. And I'm going to multiply chromium by 2. So I already have 2 chromiums over here. So I'm going to have 2 chromiums on the other side as well. Now the number of electrons gained and lost are going to be equal. Is this clear?
Yes.
Yes, sir.
And then you can balance the oxygen, and the only 2 things that are not balanced at the moment are the ones that were not involved in this redox reaction. So they're not balanced. So we're gonna just balance them the usual way, which is that you got how many oxygens? You got 9 oxygens on this side, and there's 7. So there are 7 over here. So sorry, there are 6 over here. And there's 7 on this. That's 13 oxygens. So I need 9 plus there should be 4 oxygens over here. So I'm going to put 4 next to it. And we can then balance the hydrogens. So on the right side, I've got 8 hydrogens. Over here, I've got 3 hydrogens. So there should be 5 hydrogens over here. So the remaining things are balanced the same way, the old-fashioned way. But you have to balance the number of electrons gained and lost. And then finally, you have this whole balanced equation. TK, is this clear?
Yes, sir.
Yes, sir.
So we'll practice more of these equations probably the next class, but I'll just give you a brief overview of what to expect next, and that is that all these equations, whatever you've studied so far in redox reactions up till AS, the equation was always given to you. All you had to do was figure out who's gaining electrons and who's losing electrons and balancing of the equation. That's pretty much all you had done so far. Now, the next chapter involves how do you come up with this equation in the first place? Like, what's the logic behind that? How do you figure out, like, if the whole equation is not given to you, they just gave you HNO2 and Cr2O7, are you able to make the whole equation completely on your own? So if only these two are given, can you make this entire balanced equation? So previously the equation was always there for you, but in this chapter, the whole entire equation will be made by you. This is what you're going to learn. Okay. So I'm going to continue with this thing. We'll do a bit of more balancing, and then we'll just move to the electrochemistry chapter in A2. Okay. So let's continue tomorrow then. Okay.
ठीक है sir, thank you. Allah Hafiz.
Okay, take care. Allah Hafiz.
Allah Hafiz sir.